In this class, let us discuss how to calculate moment of inertia of some simple objects of regular shape or symmetric shape. So let us start with a thin uniform ring. Okay. So what I mean by uniform ring is its mass is uniformly distributed throughout the ring, and thin means its area of cross section is negligibly small. Okay. So essentially we can consider this as a one-dimensional object. So we have okay, let us consider a ring of radius r, capital R, mass capital M. So it's a very thin ring, so we can neglect the area of cross section. Essentially consider this as a one-dimensional object. We want to calculate the moment of inertia of this ring about the axis of symmetry of the ring, which means about the perpendicular axis passing through its center. This is the axis of symmetry of the ring. Okay. So let's try this. So since we can consider this as a one-dimensional object, what we can do is, let us consider an elemental length. Okay. Let's say dl. Let's say the mass of this elemental length is dm is equal to lambda times dl, where lambda is mass per unit length. Now this ring is a uniform ring, therefore mass is uniformly distributed throughout the ring. So what is the mass per unit length? Total mass divided by total length of the ring. Since it's a ring, the total length is the circumference of the ring, therefore since area radius is capital R, circumference is 2 pi r. So mass per unit length is capital M divided by 2 pi r, right? So we have the mass, the differential mass of the elemental length dl is m by 2 pi r into dl. Okay, so what is the moment of inertia of this ring? It is integral rho square dm, where rho is the perpendicular distance from the axis of rotation. Now in this particular geometry, when the axis of rotation is the same as the axis of symmetry, the perpendicular distance is nothing but the radius of the ring. Okay, so this is equal to integral capital R square. Instead of dm, let me substitute, so capital M by 2 pi r dl. So we are integrating over the length of the ring. Okay, it's an integration over a closed loop. Okay, so we may say that either we can use the simple integration over the closed loop, or we can say that we are integrating from one end, starting from the point 0 to ending at the same point 0. Okay, so integration over the closed loop of of this ring. Let's take the constant terms outside. Okay, so here r square is constant, m by 2 pi r is constant. So what is remaining? Closed integral dl. What is this closed integral dl? It is the total length of the ring. Okay, which means the circumference of the ring. And since the radius is capital R, circumference is 2 pi r. So this integral will turn out to be 2 pi r. 2 pi r. So we have capital R square m by 2 pi r into 2 pi r. This 2 pi r will cancel. Therefore, moment of inertia of the ring about the axis of symmetry, about the perpendicular axis passing through its center, is mr square. Okay. Let's go to the next object. So this let's consider secondly a thin, uniform disk. Okay, so it's a two-dimensional object. Okay, so we have a disk. Let's say its radius is capital R, mass is capital M. We want to calculate the moment of inertia of this disk about the axis of symmetry. Axis of symmetry means, again, just in the case of the ring, a perpendicular axis passing through its center. Okay. Now we will do this calculation in two methods. It's instructive to do this calculation in two ways. Okay. It will be useful. Learning this techniques will be useful for in different areas of physics, not simply in mechanics. So let's try to calculate this using two methods. So method 1. Okay. I will assume that a disk is composed of, or let us say we divide this disk. Divide the disk into a series of concentric rings. This is the technique. Okay, already we have obtained the expression for the moment of inertia of a ring about the perpendicular axis passing through its center. So we will use that result to obtain the moment of inertia of the disk. So we assume that a disk is composed of a series of concentric rings. Okay, so our situation is like this. This is our disk, radius capital R. Now I assume that it is composed of a series of concentric rings. Consider one such ring of radius R. I also assume that it has a small thickness. This ring has a small thickness dr. Okay. This shaded area represents the thickness of the ring. So let us say this thickness is dr. Okay, so we assume that this disk is composed of a series of rings whose radius vary from very small value, nearly zero value, to capital R, the radius of the disk. So there are a series of concentric rings of very small thickness dr. Okay, so when you draw such rings, concentric rings together, we get the disk. So what the idea is that the total moment of inertia of the disk is integral of moment of inertia of these rings. Okay, this is the moment of inertia of the disk. This is moment of inertia of each ring, di. So total moment of inertia of the disk is, you add the moment of inertia of each ring, di plus di plus di plus etc. In the limiting case, when the thickness of these rings reduced to 0, we can say that the summation becomes integration. So integral of di, where di is the moment of inertia of each ring. Now this ring, when you consider such a ring, we assume that its mass is some dm. Okay, and what is the radius? Small r. Okay, so we consider one such ring of mass dm and radius r. So if you know the mass and radius of a ring, we know its moment of inertia di. What is the moment of inertia? From the earlier calculation, what was the earlier result? Oh, sorry. Yeah, this one, a moment of inertia of a ring about perpendicular axis mr square. Okay, this was the figure mr square. So here in this particular case of the disk, our ring has mass not capital M but dm, right? And its radius is r. Okay, so what is the moment of inertia di? Dm into r square. Instead of capital M into r square, okay, instead of capital M we have dm. Instead of capital R we have small r here. Okay, instead of capital M we have dm, capital R we have small r. So the value of moment of inertia of this elemental ring is dm into r square. So what is the moment of inertia of the disk? Integral dm into r square. Now we want to find out what is this dm. What is the mass of this small ring shaded in that figure? So it is given that it's a uniform disk. Okay, uniform disk is the mass is uniformly distributed throughout the disk. So we can say that the mass of the ring, okay, I will write it here, mass of the ring of radius r, this quantity is equal to mass per unit area. Since mass is uniformly distributed, this quantity must be a constant. So mass per unit area into area of the ring. Okay. Now therefore we can write dm is equal to mass of the ring is dm. What is mass per unit area? Total mass is capital M. Total area is pi r square for the disk. So mass per unit area is m by pi r square. Here we are using the idea that mass is uniformly distributed throughout the disk into area of the ring. What is the area of this ring? Its radius is r. Look at this ring. Its radius is r. Thickness is dr. So if radius is r, circumference is 2 pi r, thickness is dr. So the area of this ring is 2 pi r. The shaded region is 2 pi r into dr, we can say. So this becomes 2 pi r into dr. Circumference into thickness. Okay, that is the area of the ring. So we have got dm. So we can substitute that value in the above expression. Therefore, moment of inertia of the disk is equal to integral m by pi r square into 2 pi r dr. This quantity is nothing but dm. We are substituting for dm into r square. Okay, and what is it that we are integrating? We are integrating over different rings. So what are these different rings? How their dimension varies? Their radius varies from 0. Okay, it's negligibly small value, nearly 0, to the radius of the disk, capital R. So the integration is from 0 to r, integrating over the rings, different rings. Okay, let us integrate this. So let's take the constant terms outside. Capital M is constant, pi r square is constant, 2 pi is constant. What is remaining is 1 r here and r square. So we have r cube dr. Okay, integration is m by pi r square 2 pi. What is integral of r cube? R raised to 4. So r raised to 4 by 4, limits from 0 to capital R. Okay, when you put the limits, what do you get? M by pi r square 2 pi capital R raised to 4 divided by 4. Lower limit gives 0 value. Okay, so pi will cancel, 1, 2 and 4 will cancel. So we have half capital M. R square and r raised to 4 will cancel. So half m r square. So moment of inertia of the disk about the perpendicular axis passing through its center is half m r square. Okay, in this method, what we have done is we have assumed that a disk is composed of a series of concentric rings, or we have divided the disk into a series of concentric rings. Now we will do the same problem using second method. Okay, in this second method, what we do is we consider the disk as a two-dimensional surface. Okay, so if you have a two-dimensional body, how do you calculate moment of inertia? Okay, for a two-dimensional body, generally what we do is for a two-dimensional body, what is the differential mass? Differential mass is mass per unit area into area, an elemental area dA. Okay, therefore moment of inertia is equal to integral rho square dm, where rho is the perpendicular distance from the axis of rotation, or perpendicular distance from the axis about which we are calculating the moment of inertia. Okay, and instead of dm we have sigma dA for a two-dimensional surface. So consider again this disk. Because of the circular symmetry of the disk, it's convenient to use polar coordinates for this calculation. So for an elemental area, I will consider a small patch from the center at a distance r from the center. Okay, consider a small patch like this. Consider this shaded region. This is our elemental area. Okay. So how do we express this elemental area in terms of polar coordinates? So this elemental area comes because when the radial distance r changes by dr and the angle changes by d theta. So this side is dr and this side is r d theta. Okay. So the elemental area in polar coordinates is di is equal to dr into r d theta, that is r dr d theta. Okay, and what is rho here? Perpendicular distance of the elemental mass, of the differential mass from the axis. So axis is again this perpendicular axis passing through the origin, passing through the center. So what is the perpendicular distance of this elemental area from the here this elemental area has the mass dm. Okay, it has the mass dm. This side is r d theta. Okay. So what is the distance of this differential mass dm from the axis of rotation, perpendicular distance? It is nothing but r. Okay, so this equation we can modify as integral r square dm. And let us substitute for dm. Integral r square dm is sigma dA. So this is a surface integral, a double integral. Okay, integral, double integral r square sigma, what is dA? R dr d theta. So this double integral involves limits of r. Limits of r is from 0 to maximum radius, capital R of the disk. This is 0 to capital R. And limits of theta from 0 to 2 pi. It should cover the entire circular plane. So 0 to 2 pi. Okay. And we need to substitute the value of sigma. What is sigma? Mass per unit area. Okay, sigma is mass per unit area. Now the disk is it's a uniform disk, that is mass is uniformly distributed. So what is mass per unit area? Total mass divided by total area, m by pi r square, r dr d theta. Okay, let's do this integration. Take the constant terms outside. Okay, m by pi r square is constant. 0 to 2 pi d theta, 0 to capital R, r square into r cube dr. This is what we have to find out. So we have m by pi r square, and this integral over d theta will give you 2 pi, and integral over r cube will give you r raised to 4 by 4. When you put the limits, we get capital R raised to 4 by 4. Okay. This is m by capital R square. By capital R square. Okay, there is look at here. Instead, in the integrand we have capital R square. So when you take it outside, it should be capital R square. Now when you simplify this, what you get is simply half m r square. The same value that we have obtained by method 1. Okay, so both method 1 and method 2 lead to the same result as it should be. Okay. So let us try to understand these two techniques now. If you have this uniform disk, in the first method what we have done is we have assumed that the disk is made up of a large number of concentric rings. Okay, and we have used So what is the total moment of inertia of the disk? It is the integral of moment of inertia of each ring. And we have used the result that for a ring of mass dm and radius small r, moment of inertia about a perpendicular axis passing through its center is dm into r square, or mr square simply. Here m is nothing but dm, differential mass, and r is radius small r. Okay, we have used that result, and from that then we have integrated over the rings. Integrated over the rings means each ring has its radius varies from 0 to capital R. So integrating over the rings means integrating over the radius of the rings. That's why we have a single integral here. We are integrating over the rings. Okay, so we get this result. And in the second method, we have not assumed any previous result of rings. We considered this disk as a two-dimensional body, as a surface, and for a two-dimensional body, this general expression moment of inertia is equal to integral rho square dm, we can rewrite as integral rho square into dm becomes sigma d. It's a surface integral. So we have taken an elemental surface area, elemental area dA on the surface of the disk, and we have used polar coordinates for simplicity because of the symmetry of the problem, and we have got the same result. Okay, you study these two results, two methods in detail. Okay, we will need this in many areas of physics. Okay, these two ways of calculating the same problem. Okay, now the third object we are going to study is a uniform thin rod, or a thin uniform rod. Thin in the sense that its area of cross section is negligibly small compared to its length. Uniform in the sense that mass is uniformly distributed throughout the rod. So we will calculate the moment of inertia of this rod about two axes. So first is we have a rod here. We want to calculate the moment of inertia about a perpendicular axis passing through its center. Okay. So what we do is consider an elemental length dl, which is at a perpendicular distance L from the axis of rotation, or axis about which we want to calculate the moment of inertia. And this assume that this elemental length dl has a mass dm, which we can write as lambda times dl, where lambda is mass per unit length. Okay, so the moment of inertia of this body we can write as integral rho square dm, where rho is the perpendicular distance of the elemental mass dm from the axis of rotation. Okay, from the figure, the perpendicular distance from the axis of rotation for this dm is nothing but L. Axis of rotation is the central perpendicular axis passing through the center, and the perpendicular distance of dm from the axis of rotation is L. So instead of rho we can use L. Rho is equal to L in this case. So L square, what is dm? Lambda dl. And what are the limits of integration? Since the axis is passing through the center, we can assume that the coordinates at the center is 0. So this end is minus L by 2, this end is plus L by 2. The total length of the rod is capital L, and its total mass is capital M. Okay, so the limits are from minus L by 2 to plus L by 2. Okay, so what is lambda? It is given that this is a uniform rod, that is mass is uniformly distributed throughout the length of the rod. So mass per unit length is total mass divided by total length into dl. So we can integrate this, take constant terms outside, m and capital L are constant, minus L by 2 to plus L by 2, L square dl. Here we can use a result from mathematics that if you integrate an even function about symmetric limits, okay, for example here the integrand is L square, which is an even function. We are in the integration is over a length of the rod, so L square is an even function. When you integrate an even function over symmetric limits, we can rewrite this integration as 2 times 0 to L by 2 L square dl. Okay, this makes it simpler. Even if you don't do this, if you don't take this substitute in this step, we will get the same result. Okay, that you can check without taking this step, 2 times 0 to L by 2. You can do this calculation and you will get the same result that you can check. Okay, let's come back to here. So we have 2m by L. Let us integrate this. L square, we integrate L cube by 3, limits from 0 to L by 2. If you substitute that value, what you get is instead of small l, if you substitute capital L by 2, you get L cube by 8. Okay, so in the denominator you have L cube by 8. So in the denominator we have 24. 2 will cancel with 24. So you have 1 by 12 capital M. 1 L and L cube will cancel. So we have L square. So moment of inertia of a thin rod about a perpendicular axis passing through its center is 1 by 12 ml square. Okay, that's the result. So you can check again whether instead of taking this particular step 2 times 0 to L by 2, if you do the integration directly, whether we get the same result. That you can check. You should get the same result. Okay, so now in this particular calculation we have taken the axis about which the moment of inertia is calculated as the perpendicular axis passing through the center. Consider another axis. So consider a situation like this. You have a thin rod. You want to calculate the moment of inertia about a perpendicular axis passing through one end of the rod, like this. Okay, here what we have to do is take the coordinate of this end as 0 and this end is L. Again you have an elemental mass dm. Here you have an elemental length dl. So dm is equal to lambda times dl, and the perpendicular distance of this elemental mass from the axis is L. Okay, so the procedure is the same. Moment of inertia is equal to integral rho square dm, and here rho is again equal to L, perpendicular distance from the axis. So integral L square, and what is dm? Lambda dl. What is lambda? Mass per unit length into dl. What is the limit of integration? From 0 to L. That's the difference. Here earlier we considered it as from minus L by 2 to plus L by 2. Here it is from 0 to L. Take m by L outside. So we have integral 0 to L, L square dl. What is the result? M by L, L cube by 3. So we have 1 by 3 ml square. Moment of inertia of the rod about a perpendicular axis passing through one end of the rod is 1 by 3 ml square. If it is an axis passing through the middle of the rod, we have 1 by 12 ml square. Okay, these two ways of calculating the moment of inertia of the same rod, same object about two different axes, it again shows that we know this result from earlier problems, but this also shows that moment of inertia not only depends upon the upon the object, upon the mass of the object, but it also depends upon the distribution of the mass about the axis of rotation. Okay, so the choice of axis of rotation is important. If you choose the axis of rotation, in the case of this rod, if you choose the axis of rotation as the central perpendicular axis, moment of inertia is 1 by 12 ml square. If it is the axis of rotation is a perpendicular axis through one end, you have moment of inertia is different, 1 by 3 ml square. Okay, so it depends upon the axis also, not simply the object or the geometry of the object. Okay, so that is our third object. Now we go to one more case, fourth case. A uniform spherical shell. So we have a uniform spherical shell Uniform means mass is uniformly distributed. It's a hollow sphere, okay, or a shell. So a shell you can consider as a surface, that is a two-dimensional object. So its mass is m, radius is capital R. We want to calculate the moment of inertia about a perpendicular axis passing through the center of this spherical shell. So how do we make this calculation? You consider a small patch of area, elemental area on the surface of the shell. Okay, let's say its mass is dm. Mass you can write as mass per unit area into elemental area dA. So what is the distance of this, since it is on the surface, what is the distance of this patch from the center? It is capital R. Assume that I am drawing this patch on the surface. Consider our shell as a balloon, a spherical balloon, and this patch is on the or a football, and this patch is on the surface of that balloon or football. So its distance from the center is capital R. This is our axis, axis passing through the center. So what is the perpendicular distance of this patch from the axis? This is rho, right? This quantity is rho. This angle, it's polar angle theta. You can this perpendicular axis you can take as the z axis. So the polar angle theta measured from the z axis is, okay, its value is theta about for this elemental area. Therefore, from this figure, it is clear that this perpendicular distance rho is r sine theta. Okay, and dm is equal to sigma dA. And what is the elemental area dA? Here we can use spherical polar coordinates. In spherical polar coordinates, the elemental area dA is, it's a theta phi plane, we can say. Its value is capital R square sine theta d theta d phi. Okay, so we can substitute all these values. So moment of inertia is integral rho square dm, which is integral. What is rho square here? Rho square is r square sine square theta. What is dm? Sigma dA, right? So sigma times dA. This is rho square. Sigma times dA. What is dA? R square sine theta d theta d phi. So it's an integration over a surface. You have two variables here, theta and phi. Theta varies from 0 to pi and phi varies from 0 to 2 pi. Theta is the polar angle and phi is the azimuthal angle in spherical coordinates or spherical polar coordinates. Okay, what is sigma here? Sigma is mass per unit area, right? Now this is a uniform shell, so mass is uniformly distributed. So let us calculate sigma r square sine square theta. Sigma is total mass divided by total surface area. What is the total surface area? 4 pi capital R square. Okay, then r square sine theta d theta d phi. Take all the constant terms outside. R raised to 4, right? Then m by 4 pi r square. Then integration over phi is 0 to 2 pi d phi. Integration over theta is 0 to pi. You have sine square theta into sine theta here. So sine cube theta d theta. Okay. And integration over 2 phi will yield, integral d phi will be phi. When you put the limits, you get 2 pi. Okay. And integration over theta, this integral sine cube theta d theta, this I am giving as a homework. You evaluate this integral 0 to pi sine cube theta d theta. There are different ways of doing this calculation. You can try that, and the result is, I will quote the result. This is 4 by 3. Okay, you can try to do this. So what is the moment of inertia of the spherical shell? let us do sum up all these things. M by 4 pi r square. Here you have 2 pi from the integral over phi, and from the integral over theta you have 4 by 3. Okay, right. So what you get is 4 pi will cancel, 4 will cancel. So we have 2 by 3 m. R square and r raised to 4 will cancel. So we have 2 by 3 m r square. So moment of inertia of a spherical shell about an axis passing through its center is 2 by 3 m r square. Moment of inertia of a uniform spherical shell. Okay. Now let us consider one last object. This I will give as a homework again. So fifth one, a uniform sphere. So now you understand what is the meaning of uniform. Mass is uniformly distributed. Okay. Now I want you to calculate moment of inertia of a uniform sphere. Consider a uniform sphere of mass m, radius capital R. Calculate the moment of inertia about an axis passing through its center. Okay, this is similar to the previous problem of spherical shell. Only difference is that that was a hollow sphere, a spherical shell, a two-dimensional surface, whereas this is a uniform sphere, a three-dimensional surface, a three-dimensional object. It's okay. So I want you to do this problem in two ways. In method 1, calculate moment of inertia of the sphere by considering the sphere as composed of a series of concentric shells. Okay, you know the result of a spherical shell. Okay, we have done this calculation. Okay, we have done this calculation here for a spherical shell. Moment of inertia about the axis passing through its center is 2 by 3 mr square. You can use that result. Remember that we have done this type of a technique in the case of a disk. We have assumed that a disk is composed of a series of concentric rings. In the same way, you assume that the sphere is composed of a series of concentric shells. Okay, you can say that this shell has a radius and a small thickness. Okay, then such shells, if you draw close together, you will get a sphere. Okay, so you consider the sphere as composed of a series of concentric shells. Use the result of spherical shell that we have obtained earlier in the previous step, and then you do the calculation of the sphere. Okay, you integrate over these spherical shells to get the result of the sphere. That is method 1. Now in method 2, what you have to do is consider this as a three-dimensional body. For a three-dimensional body, how do you write you take a differential mass? Okay, how do you take the differential mass? You can write as mass per unit volume into the differential volume d. Okay, so the point is that in this sphere, you take a differential mass, let us say like this. Its volume is dv. This is our axis. Now this differential mass you take at a distance, let us say small r from the center. Okay, so you have to calculate the mass per unit volume, and for this you can use the idea that it's a uniform sphere. Mass is uniformly distributed. And what is the elemental volume here? You can use spherical polar coordinates. elemental volume at a distance r from the origin is r square sine square theta dr d theta d phi. Not sine square theta, r square sine theta. So square is not there. R square sine theta dr d theta d phi. Okay, this is the volume element in the um, spherical polar coordinates. Okay, and so you have dm, then you can moment of inertia you can write as integral rho square dm. What is rho here? Perpendicular distance from the axis of rotation. So here this elemental volume is at a polar angle d theta. What is a perpendicular distance from the axis of rotation? You can think about it. It's not r, but what is a perpendicular distance? You can think about it. What is rho? So you can substitute this rho here, get it from the figure, and dm here, dm is w into dv, and dv I have written. What is w? Mass per unit volume. For that you have to use the idea that it's a uniform sphere, mass is uniformly distributed. So from that you can figure out what is mass per unit volume. So substituting all these values you do. So this will be a volume integral. Okay, it's a triple integral. What are the three variables? R, theta and phi. So you put the proper limits for r, theta and phi. Okay, and now you already know the limits of theta and phi. What is the limit of r? You can figure out. Do this integration as a triple integral, as a volume integral, and in these two methods you should get the same result. Okay, I am not giving the result now, so you do this calculation as a homework. So far we have done calculation of moment of inertia of this homework, including this homework we have considered 5 objects, a thin uniform ring, moment of inertia about and a perpendicular axis passing through its center is mr square, then a thin uniform disk, moment of inertia about the central axis, perpendicular axis, half mr square, then moment of inertia of a rod, if it is a perpendicular axis through its center, 1 by 12 ml square, if it is a perpendicular axis at one end, 1 by 3 ml square. Then moment of inertia of a spherical shell, which is 2 by 3 mr square, right? 2 by 3 mr square, about an axis passing through its center. And finally the fifth object is a uniform sphere. Okay, this value you have to evaluate. Okay, let's stop there.